All right, so I split this into two videos here. But here we go. Graph C right here. So I'm going to go ahead and look at what's going on here. As time increases, my distance doesn't change. So as time increases, the distance doesn't change here. So what does that describe of these right here? Well, that's going to be the car is stopped. That's going to be description 1 here. And then I'm going to just describe this last one. This one's a little hard to see. But as time increases, we always look at that right there. So as time increases, what's happening? I'm going forward, right? I'm going to more distance, but I'm not going as covering as much distance as time increases, right? So I'm going forward, but what's going on? Since I'm going less and less, I'm slowing down, but slowing, right? Because I'm covering less and less distance as time goes on. So which description is that? The speed of the car is decreasing. So imagine this is like if I'm traveling at 35 miles per hour, driving down 116, and I see a red light. So I'm moving forward. I'm going at good speed right here, but then I need to slow down. So I'm still moving forward, but I'm covering less and less distance as time progresses right there. Okay, so that's going to be right here. The speed of the car is decreasing, description 3. All right, so then I'm going to go forward here. That was our distance versus time graphs. Now I want to look at speed versus time graphs. So speed versus time, also called velocity versus time graphs. If we have a straight line, a horizontal line right here, what is this telling us? Well, this is a lot different than distance versus time. Distance versus time meant that it was standing still. Now, if it's a speed versus time, this just means we're moving at a constant speed, right? So if this was 7 miles per hour, I'm staying at 7 miles per hour. No matter what the time is, I'm always at that 7 miles per hour. If the speed is going up, so as time increases, if the speed is increasing, we call that our acceleration. Okay, an object is accelerating forward. Okay, and the opposite, if it is time increases, the speed is going down, we call this deceleration or a negative acceleration. We can also, just like we did with distance versus time, we compare the slopes. We compare the slopes here. And what this means is the greater the slope, the greater the acceleration here. So we can summarize this as if we see as time increases, if the speed goes up, it's accelerating. If the speed is a horizontal line, that means it's at a constant speed. A smaller acceleration here. But why? Because we know this is a greater slope here, a smaller slope here. And this would be a negative acceleration or deceleration right here. So we're going to go ahead and try to match these with it right here. So if I look at graph E, if you want to, you can go ahead and try and pause this. I'm just going to go ahead and keep going. So pause it if you want and try to fill this out. All right. So graph E, again, I always start with as time increases, right? We want to look at just what happens as time increases. That means as I'm going across my x-axis right here, well, as I go across, the speed increases, right? So that must be the car is accelerating. It's getting faster. The increases, the speed increases. This is our just definition of acceleration, right? So as time increases, speed increases. Graph F. Okay, so as time increases, what's going on? As time increases, the speed decreases. So this is our textbook definition of deceleration or negative acceleration here. So I'm going to put here the car is slowing down. Okay, I'm going to go to graph G here. So as time increases, the speed doesn't change. The speed is staying the same. So as time increases, the speed remains constant. So that's going to be not the car stopped, but it's traveling at a constant speed here. So that's going to be 6. Now this is the special case of as time increases, there is no speed. So as time increases, there is no speed. And that's going to be 5 right there. The car is stopped. All right, go ahead and get those down. Pause if you need to at any time. All right, so now I've got a graph here with 3 different runners, and it wants us to evaluate what's going on in this graph. So now that we're really getting to the core of it, why we want to do this, graphs really help us understand real life examples of what's going on in the world. So this is a 100-meter race right here. I know that because this is my distance. It's in meters right here. It goes up to 100 meters. My time right here is down here. This is in seconds. It goes up to 18. So if I look at the graph, it shows 3 runners ran a 100-meter race. Which one to run the race? Explain your answers. Well, I got Albert, Bob, and Charlie. They're all 100 meters, right? They all got to this 100-meter mark here. So who won the race? Well, who usually wins races? It's whoever gets done the fastest. So I look at their times. Albert got done 12 seconds, Bob 14, Charlie 16. So because Albert got done 12 seconds, he would have won the race. So I'm going to put Albert because he finished in 12 seconds, and in parentheses, the fastest time. Right? Which runner stopped for rest? So if we look right here, rest, this is a distance versus time graph. So rest just means that it's non-moving. So if I look at here, Albert, nice parabolic shape, doesn't change. Bob, nice parabolic shape. Charlie started really strong, was winning the race until about 8 seconds, and then maybe he just tripped and fell, and he stopped for a bit. So Charlie, right, because he has that flat line. So Charlie, he stayed at, and if I look right here, this is between 40 and 60, so I'm going to say he stayed at 50 meters for a few seconds. And this says, well, how long was that? Okay, so I can get the exact time here. It looks like he stopped right here at 8 seconds, and it went to about between 12 and 14, so 13 seconds. So 13 minus 8 is going to be 5 seconds. So Charlie stopped for 5 seconds. All right, how long did Bob take to complete the race? So now we're looking at Bob. I just need to figure out when he reached the 100-meter mark. That's going to be 14 seconds right here. So Bob finished 14 seconds. All right, and calculate Albert's average speed. So we just have to remember here, speed is just equal to average speed is equal to total distance over the time. So if I look, I know it's a 100-meter race right here, and then it finished in 12 seconds. So I can go ahead and put that in as 100 meters divided by 12 seconds. And that's going to give me 8.3 meters per second right there. Okay, so I can go ahead and calculate all three of these if I wanted to. I just take their average distance over the time that it took them to get there, and I get their speed. Albert was the fastest, though, with 8.3 meters per second. All right, last thing we're going to do here. Graph below shows the speed of a bus changes during part of the journey. So choose the correct words from the following list to describe the motion during each segment of the journey to fill in the blanks. So I got segment A here. So from 0 to A. What's going on? So as time increases here, what's happening to my speed? This is a speed versus time graph. My speed is increasing. So if my speed is increasing, do I call that accelerating, decelerating, constant speed, or S? I'm going to call that accelerating, right? As speed increases over time is acceleration. So the bus is accelerating from 0 to A. Then I'm looking from A to B. So it starts at 10 meters per second. It ends at 10 meters per second. So what's it doing? It's staying at a constant speed here. And then B to C here. So I'm going from 10 to 13 right here. Okay, as time increases, my speed is decreasing. So we're going to call that a deceleration. We're decelerating right there. And C to D here. So C to D, I start at 0, I end at 0. So this is going to be stopped. And the last one here, DD, I'm starting at 0. I end at about 5 meters per second. It's increasing. So this is accelerating. Okay, hopefully that makes a little sense. And you can go ahead